This is video lesson number 9, looking at types of reactions. So, describing reactions. Some chemical reactions can be really useful and really helpful. They can create substances that are good for us, like making different types of drugs, but they can also be very harmful. So some reactions can be very violent, let off a lot of heat energy, or can be corrosive and burn things. You have to be really careful. They can produce gases that can be really toxic as well. So we need to make sure that we can categorize our reactions and understand which ones are going to be dangerous and which ones are going to be useful for us to do to produce new things. So to keep track of all the reactions, okay, we need to describe reactions in a way that's easy to read. So it has to be really easy to understand. Okay, and then we organize the reactions into groups. So similar reactions are grouped together to help us better predict the products of a reaction. So chemical reactions are grouped by the products produced. There are 5 types of reactions. So synthesis, decomposition, single displacement, double displacement, and combustion. So we're going to go through each of those types and talk about the characteristics of each one and how we can identify them. So we can better understand experimental observations of the behavior of substances when we know and understand the different types. And we can also use this information to predict the products of a reaction. So if you have 2 things that you mix together and you don't specifically know already what you're going to be producing, by figuring out which type of reaction it is, you can then predict what product you're going to make. So the first type is called synthesis reactions. Now the word synthesis, think of synthesizing something or making something. And these are characterized by having a single product. Okay, so they only form one product. So your description here, elements or small molecules are going to combine together to form a compound. So here we have a single product. So an example that we're going to look at is magnesium and oxygen. So in a reaction between magnesium and oxygen, we're going to have Mg as magnesium plus oxygen is part of that Hofbrinkel group, so it's O2. And in a synthesis reaction, you're making one compound, so we're going to be putting those 2 things together to make magnesium oxide. So again, this is an ionic compound, so I'm figuring that out by doing the crisscross method. I know it's 2 and 2, which reduces to 1 and 1 to give me MgO. Okay, so naming this is magnesium oxide. And last step here, we should balance our reaction equation because we should always do that. So 2 oxygens on this side, so we need 2 on the product side. That changes the number of magnesiums to 2. So 2 magnesiums there. So now it's balanced. So we can see here we have 2 elements coming together to form a single product. Let's do another example and then we'll come back to that. So example number 2, we have iron and oxygen. So this is the reaction of iron rusting on cars and various other places. So iron symbol is Fe plus oxygen O2, forming iron oxide. So FeO. No, I'm saying it's forming iron 2 oxide. It could theoretically form iron 3 oxide, but iron 2 is a little bit more common than iron 3, and it has to do with a lot of other things that are far more complicated and beyond grade 10. So in a situation like this, if you were given a reaction like this, you could choose whichever of the multivalent versions you wanted to, and they would be marked as correct as long as you choose one that actually exists. So, you know, you wouldn't want to predict that it's going to make iron 1 oxide because iron 1 doesn't exist. So in this case, if I say I've got iron 2, I'm going to balance this out again by putting a 2 in front and behind, and I'm going to finish my word equation. So iron plus oxygen forming iron 2 oxide. So 2 elements coming together to form a single product. Our general sort of formula or equation for this type of reaction that you'll see this pattern happening over and over again is you'll have A plus B forming AB. So you've got 2 pieces coming together and sticking together to form a single product. All right, moving on to the next one is decomposition. So decomposition, think of, you know, compost or decompose. So it's the idea of something falling apart or breaking apart into multiple pieces. So an example here, we have ammonium dichromate. Now in this reaction, this is a picture of it. When you catalyze this reaction by taking the ammonium dichromate and just introducing a little bit of heat, it sort of makes this volcano-esque looking thing. You can YouTube that reaction, decomposition of ammonium dichromate. It's a really good one to see. We would normally do that in the lab if we were able to. Unfortunately, we're not in this case, but this is kind of what it looks like. But the idea remains the same. You have a single product or reactant, in this case ammonium dichromate, that's going to break apart into a few different pieces. So ammonium dichromate looks like this. So this is a compound that you wouldn't already know how to name yet. So ammonium is a polyatomic ion. Chromate, dichromate is another polyatomic ion, not one that we worry about or use in grade 10, but so it would be a solid. Okay, and it's going to break apart into 3 different pieces. So it's going to form chromium oxide, which is Cr2O3. It's also going to form nitrogen gas, so N2, and water, H2O. So this is one single reactant breaking into multiple products. So the way that we can recognize this really easily is by a single reactant. We'll finish off the word equation. So forming chromium oxide I missed the H in chromium. Just fix that. Chromium oxide plus nitrogen plus water. And we should balance our equation. So in this case, if you look at it carefully, it's actually already balanced. So we have 2 nitrogens there, so there's 2. We have 2 times 4 is 8 hydrogens. Oh, it's not already balanced. 8 hydrogens, we need more over here. So we need 4 in front of that, so that gives us 8. Then 2 chromium, so 2 there. And then we've got 7 oxygens, 2 plus 4 times 1 over here is 4, is a total of 7. So there we go. General formula for these is going to be AB falls apart into A plus B. So a single reactant breaking apart to form 2 or more. So 2 or more products. Now these products could be single elements, sort of like it looks like in here, or it could be more complex small molecules, like we see in the example. The next type is single displacement. So the identifying features of a single displacement reaction is that you have a single element reacting with a compound. So those are the reagents involved. So it's easiest to see if you're looking for a single element plus a compound in the reactants and in the products, really. So our general formula would be something like AB plus C, where let's say C is a metal, it would replace A, so we would end up with A plus CB. So if C is a metal, then A and C, A is also a metal, are going to basically switch places. So it's C is displacing the A and taking its place. Now this can only happen if the metal that's on its own, that's doing the displacement, is more reactive than the metal that's in the compound. So you'll see there's a chart over here that has a list of metals in it. This doesn't contain all the metals, but it gives us a good idea of a few of the most common ones. And a metal can only displace another metal lower on the list. So if we do an example here, silver nitrate plus copper. Silver nitrate is AgNO3 plus copper is Cu. Copper is here, silver is here. Copper is higher than silver on the list, which means that it basically has enough reactivity to push the silver sort of out of the way. So the copper is going to take the place of the silver. And that's going to give us copper nitrate, so copper 1 nitrate, plus silver on its own. So this is already balanced. To finish off the word equation, we would name this copper 1 nitrate plus silver. So that's the depiction of the picture here. You've got a copper wire going into a solution of silver nitrate, and you can sort of see the fuzzies building on there and the blue color starting to show up. The blue color is because copper in solution is blue, so it's starting to turn blue. The longer you leave that copper in there, the more blue it will go. And then the silver is starting to precipitate out of solution and form solid silver on its own. And it's sort of attaching to that, but it'll fall off and sort of sit on the bottom. Okay, so single displacement, you have a single element reacting with a compound. If the single element is more reactive than the one in the compound, then they switch places. If the element that's on its own is not more reactive than the one in the compound, then there would be no reaction that takes place. And if that happens, then you would just write no reaction on the other side of the arrow. All right, two more types. The fourth one is called double displacement. So again, we have a displacement or a switching of the arrangement of the atoms. And double, think of double is two. So instead of a single thing switching, you basically have two things switching. So a double displacement reaction involves two compounds. So you can't have any single elements for this to happen. They have to be mixtures or full compounds or molecules. Okay, so a compound reacts with another compound, okay, and the elements switch places to form two new compounds. Okay, an important note for this one is that a positive metal ion in one compound has to combine with the negative ion of the other compound. So you can't have two metals sticking together. You still have to have, in your products when you're figuring out what those are, you still have to have a positive and a negative ion in each of the compounds. So our general formula here would be AB plus CD, where let's say C and A, because they're first, those are the two metals, they're basically going to swap places with each other to form CB plus AD. So the important thing again here is a positive ion and a positive ion are switching places so that we still have a positive and a negative and a positive and a negative in our products. We don't want our metals stuck together. So an example here is lead nitrate and potassium iodide. That's the picture that's shown. So lead 2 nitrate would be PbNO3 with brackets 2 plus potassium iodide would be Ki. So the two positive parts here are Pb2 plus and K1 plus. So they are going to switch places to get KNO3 plus PbI2. Now PbI2 forms a solid, and it's that yellow solid precipitate that you see in the picture. We need to balance this, so we have 2 iodines on this side, only 1 on this side, so a 2 there. We have 2 nitrates and 2 potassiums here, so we need 2 of each of those on that side. And let's finish the word equation. So this is potassium nitrate. And this is lead 2 iodide. In a double displacement reaction, if you have a multivalent metal, it will always be the same charge in the products as it is in the beginning. So if you have 2 at the start, then it will be 2 at the end. Okay, so it always stays the same in this type of reaction. Okay, the last type is combustion. And combustion is basically a reaction with oxygen. So here we're going to look at a few specific types, but basically the broad definition of combustion is a reaction with oxygen. Hydrocarbons made of hydrogen and carbon, we saw this in one of our balancing questions, are going to burn with oxygen, and they're always going to produce carbon dioxide and water. Technically, the synthesis reactions that we were looking at earlier when we were seeing magnesium react with oxygen and iron reacts with oxygen, these are also technically combustion reactions, but this one is fast as well, but this one's very, very slow. But they're a slightly different type, so they're forming an oxide that's like a metal oxide. In this type of combustion reaction where we're reacting with hydrocarbons, so carbon and hydrogen, we have all nonmetals, and so we're forming oxides, but different types. So carbon dioxide is an oxide, and then water is also really an oxide compound. Oxide compounds are just compounds that contain oxygen, so water has an oxygen in it. So a general formula for this type is CXHY, where X and Y could be kind of any number, not like any in the whole world, but it could be any compound that's like that. Okay, plus oxygen will always be O2, and it will always form carbon dioxide, CO2, and water, H2O. So these ones are very, very similar always. The tricky part with combustion reactions is balancing them properly. It can be kind of tricky. So in our example here, we have butane. We haven't learned about organic chemistry nomenclature stuff. You won't do that until grade 11 or grade 12. But if I was going to give you a reaction like this, I would tell you what the formula of butane was. So butane is C4H10 is the formula for butane. So plus oxygen, so O2. We're going to form carbon dioxide and water, so CO2 and H2O. Finish the word equation as well, carbon dioxide plus water. And now we need to balance it. So this one's a bit of a tricky one to balance. So carbon here, I'm going to do it the long way just to make it really clear for anyone who has any troubles with balancing. We've got carbon, hydrogen, and oxygen as our elements that we're going to be working with. Start by listing them out and counting out the original amount. So 4, and then 10, and then 2 on that side, and then 1 carbon, 2 hydrogens, and again we've got 3 total oxygens, so 2 plus 1. So the first step is to do carbon. We want to leave oxygen to last. So 4 here, we need 4 over there. That's going to give us 4. But that changes the number of oxygens. So 4 times 2 is 8, plus 1 is 9. Next, we've got hydrogen. We have 10 on this side, 2 on that side. So to get 10 over here, we would multiply that by 5. Which also affects the number of oxygens. So 8 now plus 5 is 13. But we run into a problem here with this, and that is we're getting a number of oxygens, 13, that's odd. Okay, so it's not divisible by 2. And we don't want to write 6.5 in here. Your coefficients should always be whole numbers. So the way that we fix this so that we can end up with a whole number here is we're basically going to multiply everything by 2. So we're going to make this 5 a 10, we're going to make the 4 an 8, and we're going to make there be a 2 in front of this. So this makes that 8 and 8, 20 and 20. So let's kind of catch up on that. So now we have 8, 20, and 2. Here we have 8, 20, and our new number here is now 8 times 2 is 16, plus 10 is 26. And once we have 26 oxygens, that's now divisible by 2. So we can put 13 in front of the oxygen to get 26 oxygens. If you want to kind of know a shortcut to figuring out whether you're going to need that 2 in front or not, is if you take the number of hydrogens and divide it by 2, if you get an odd number, you're going to need to put the 2 out in front to make it balance. If you divide the number of hydrogens by 2 and you get an even number, then you should be able to balance it without putting anything in front of the compound there. So some practice on the next page. You're going to identify the type of compound as described by the reaction or the pictures and diagrams. The answers to this page, number 33, are posted, so you can check your work. You can also go back to all those balancing questions from the last lesson, and there is a line there to indicate the type of reaction for those. So go through those questions as well and see if you can categorize each one into one of the 4 or 5 types of reactions. Again, the answers to that are posted so you can check your work.